Unraveling the Mysteries of sklearn's Stacking Classifier, a deep dive. The stacking classifier in scikit-learn is a powerful ensemble method that combines multiple Bayes estimators classifiers to create a more robust and accurate prediction model. It excels in situations where individual models struggle to achieve optimal performance but can be leveraged collectively for significant gains. Let's delve into the intricacies of this intriguing ensemble technique. 1. The underlying principle. Stacking, also known as stacked generalization, is a meta-learning approach that builds upon the predictions of multiple Bayes models. Instead of simply averaging their outputs like in bagging or boosting, stacking classifier trains a final meta-estimator on the predictions of the Bayes models as features. This allows the meta-estimator to learn complex relationships between the individual model outputs, potentially achieving superior performance compared to any individual Bayes model. 2. Key components of stacking classifier. Bayes estimators. These are the individual classifiers that provide the initial predictions. They can be any valid scikit-learn classifier like decision trees, e.g. decision tree classifier, support vector machines, e.g. SVC, logistic regression, e.g. logistic regression, neural networks, e.g. MLP classifier, ensemble methods, e.g. random forest classifier, gradient boosting classifier, meta-estimator. This is a final classifier that learns from the predictions of the Bayes estimators. It can be any valid scikit-learn classifier, often a simple one like logistic regression, e.g. logistic regression, linear SVC, e.g. linear SVC, decision tree classifier, e.g. decision tree classifier. Final predictor. This is the composite model that combines the predictions of the Bayes estimators and the meta-estimator to generate the final prediction. 3. The stacking process. 1. Training. The Bayes estimators are trained on the training dataset. Predictions from each Bayes estimator are generated for the training data and optionally for a validation set. These predictions are then used as features to train the meta-estimator. 2. Prediction. For new unseen data, predictions are made by each Bayes estimator. These predictions are passed to the trained meta-estimator, which generates a final prediction based on the combined Bayes model outputs. 4. Building a stacking classifier in sklearn. Python. From sklearn, ensemble import stacking classifier. From sklearn, linear model import logistic regression. From sklearn, tree import decision tree classifier. From sklearn, neighbors import k-neighbors classifier. From sklearn, datasets import load iris. Load the dataset. Iris load iris. X iris. Data. Y iris. Target. Define Bayes estimators. Estimators. LR. Logistic regression. DT. Decision tree classifier. KNN. K-neighbors classifier. Define meta-estimator. Meta-estimator logistic regression. Create stacking classifier. Stacking CLF stacking classifier estimators. Estimators. Final estimator meta-estimator. Train the model. Stacking CLF. Fitix. Y. Make predictions on new data. New data. Predictions stacking CLF. Predict new data. 5. Advantages of stacking classifier. Improved accuracy. Stacking can often achieve higher accuracy than individual Bayes models, especially when the Bayes models are diverse and complementary. Robustness. Combining multiple models can mitigate the impact of noise and outliers, leading to a more stable and reliable model. Leveraging diverse models. Stacking can combine different types of models, allowing you to leverage the strengths of each and compensate for their weaknesses. 6. Disadvantages of stacking classifier. Complexity. Stacking can be more complex to implement and tune compared to simpler ensemble methods. Computational cost. Training multiple base models and then the meta estimator can be computationally expensive. Overfitting. If the meta estimator is overfitted to the training data, the overall model performance may suffer on unseen data. 7. Important considerations. Base model selection. Choosing diverse and effective base models is crucial for successful stacking. Meta estimator selection. The meta estimator should be chosen carefully to learn the complex relationships between the base model outputs effectively. Hyperparameter tuning. Proper hyperparameter tuning for both base models and the meta estimator is essential to optimize performance. Data splitting. Using cross-validation techniques during training and evaluating the model on a separate test set are essential to avoid overfitting. 8. Real-world applications. Credit risk assessment. Combining various risk prediction models to improve accuracy and robustness. Fraud detection. Leveraging different fraud detection algorithms to enhance model performance and identify complex patterns. Medical diagnosis. Combining medical imaging analysis, patient history data, and other medical insights to improve diagnostic accuracy. Natural language processing. Combining different NLP models to improve text classification, sentiment analysis, and other tasks. Conclusion. The stacking classifier in scikit-learn is a powerful tool for building ensemble models that can achieve high accuracy and robustness. By combining the predictions of multiple base models and learning complex relationships between them, stacking classifier offers a promising approach for many machine learning tasks. Careful selection of base models, meta estimator, and effective hyperparameter tuning are essential for optimal performance. The application of stacking classifier extends across various domains, enabling better decision making and problem solving in complex scenarios.